Hello, I'm Vila, and today I'm going to talk about how to enforce code conventions and streamline pull requests across big teams using static analysis. So when I first joined Line, I noticed I was joining a very big team. We can think of teams as small social groups with its own culture. Big teams bring challenges, and some of them are onboarding new members. New members usually make the same type of mistakes when submitting a PR due to unfamiliarity with the best practice in the new team. Code consistency. The bigger the team gets, the more difficult it is to ensure code consistency across the team. A lot of communication is required, so static analysis can reduce this overhead in communication. Code conventions. It is hard to ensure the whole team is using the same conventions, especially if the team is working in different geographical locations and working in different features. Internal APIs. Sometimes the same functionality is required in different features, but the team members don't know the functionality already exists. In this talk, I'm going to focus on code conventions, but we're using Lint to help with all the previous problems. As you can see, there are many commits fixing the code conventions, and a lot of them were mine. Let's take a look at this function. This code compiles, but if I ask you what's the return type of the function, you'll probably struggle. To ease code reviews, we have a code convention in our team to explicitly declare the return type of the functions. In this case, the return type is a nullable integer. I know there is an option in Android Studio to show return types, but during code reviews, having the type explicitly declared will help the reviewer to better understand the code. Okay, so what can we do to ensure the team members don't forget to explicitly declare the return type of the functions they write? As you might imagine, we're going to use a static analysis. We're going to analyze the code syntactic tree to find problems in our code base. There are many static analyzers like KT-Lint, Detector, etc., but we decided to use Lint for the following reasons. It is compatible with Java and Kotlin. It means that Java and Kotlin generate the same abstract syntactic tree, and it's called Universal Abstract Syntactic Tree. Lint Client is implemented by Android Studio. This means that Android Studio is running a Lint client on every file as we write code, and it can run some of the checks on the fly. Quick fixes. In Android Studio, not only we can detect, but also suggest solutions to possible problems we find. Okay, so we're going to create a custom Lint check to let everybody know they have to explicitly declare the return type of the function they write. In order to create a custom Lint check, we have to roughly follow these steps. Create a Lint issue with a factory provided by Lint. Describe the problem we're trying to solve and why this is a problem. Register the issue so Lint can track it. It will be added to the Lint jar, and Lint will be able to dispatch the nodes to our detector. Create a detector for the issue. The detector will be in charge in analyzing the syntactic tree and determine whether there is an issue or not. This is where we're going to focus today. Report the issue. Once we found the problem, we have to report it, specifying its location, file, row, and column ranges. And optionally, we can provide a fix. As I said before, first we have to create an issue explaining what's the problem and how to fix it. In this case, the inferred type by the compiler. To create an issue, we're going to use the factory provided by Lint. This issue will be displayed by the Lint client. Both Gradle and Android Studio implement a Lint client. So in Gradle, it will be displayed in the HTML report, and in Android Studio, it will be displayed in the editor. Now, we have to add the ID. It has to be legible because it is the identifier used by suppressed Lint annotation to be able to ignore this issue in case there is a false positive. We also have to add a short description, which will be shown in the Gradle report or when hovering the mouse over the highlighted text in Android Studio, and a long description to add more details about the problem. There are several categories: correctness, security, compliance, performance, and so on. We're using correctness because this is a code convention. This is the priority. This is just for ordering the issues. Regarding severity, we have informational, warning, error, and fatal. Fatal will break the build, so be careful when using it. Finally, we have the implementation. It points to the detector the scopes cares about. There are several scopes like Java file scope, class file scope, etc. In our example, this detector only cares about Java file scope. This is a confusing name because it also works for Kotlin. If we want to run the Lint check in Android Studio on the fly, we have to use only one scope. This basically means that all the information needed to discern whether there is an issue or not, it is within the same file. If we need to cross-reference with another file like layouts, etc., the check won't run on the editor, and it will work in the Gradle task, for example, running in your CI. Now that we declare an issue, we have to register it, adding it to the list of issues. In this case, our My Detector only detects one issue. Note that we're using AutoService to load our registry into the Lint jar, so Lint can locate our issues and run the corresponding detector. So now that we declare our issue, we need a detector to find it. A detector is responsible for detecting occurrences of an issue in the source code. Lint has a number of detector specializations, which makes a lot easier to write checks. By using these interfaces, Lint can be more efficient because it can map what to do with each node in one pass of the syntactic tree. Xml Scanner lets you visit the XML file with DOM. Source Code Scanner is useful for Kotlin and Java analysis. And there are other useful scanners depending on your needs. So we're going to use a source code scanner since we're going to analyze Kotlin code. This interface has many useful callback functions, as just to name a few, applicable superclasses. So this will call us back if the current class is a subclass of one of the specified superclasses. For example, if we're interested in analyzing every class extending an activity, we will use this method. GetApplicable method names will call us back when any of the methods in the list is called. This is what Timber uses to report when we use the Android log instead of Timber. GetApplicable UST types, it will call us back whenever Lint finds any of the provided UST nodes. So now we have everything we need to detect the inferred type of the functions. Since we're interested in analyzing every method declared in our codebase, we're going to tell Lint we only want to visit U method nodes of the syntactic tree. These U methods will be dispatched to our UST handlers visit method. Since this detector is specific for Kotlin, we're only interested in Kotlin nodes. Now that we know that the U method is Kotlin, let's check if the compiler inferred its return type. U methods give us an abstract representation of the node. Right now, we just know the node is a method. In order to know if the method is explicitly declaring its return type, we have to use a concrete representation of the node. We're using the node's PSI to check Kotlin's specific syntax. We can check whether the method has a colon or not, a fun keyword, etc. And all this concrete representation is in the node's PSI. So to recap, we told Lint we want to visit every method node in the syntactic tree by using GetApplicable UST types. If the node is not Kotlin, we're not interested in it, so we early return. Once we know the node is Kotlin, we can access to its PSI to check Kotlin's specific syntax. If we detect the return type of this method is being inferred, we report it. In order to report a node, we need the issue we previously created, a location, which is basically a file, a line, and a column range, and a message. The location will be used to highlight the code in the editor or in the HTML report. We're using getLocationName to highlight the node's name. This is how it looks in Android Studio. As you can see, we're only highlighting the method name. This is the message we use to report the problem. And in this case, we can provide a quick fix since we know the return type is of this function. Note that this ID is the one we used previously in the issue, so we can suppress this Lint rule in case of a false positive. And these are some of the examples of Lint checks we're currently using. So for example, we're extending a specific fragment within a package, avoid nesting too many lambdas, top class level comments, so when you create a new class, you don't forget to add documentation about it. And we're also working on detecting circular references in dynamic modules. I created a gist with all this code so you can check in more detail. And yeah, that's all for me. Thank you so much.